Imagine a star so bright and easy to spot in the night sky that it guided navigators for centuries. Yet when studied closely, it leaves even scientists completely puzzled. This is Polaris, the famous North Star. What seems to be just a fixed point in the heavens actually hides secrets that challenge our very models of the universe. Its age doesn't add up, its distance is an enigma, and its pulsations are unpredictable. Today, you're going to discover 10 amazing curiosities about Polaris, the most confusing star in the sky. The star that never moves in the sky, Polaris, popularly known as the North Star, is one of the most iconic stars in the sky. Unlike others, which seem to drift slowly across the night due to Earth's rotation, it remains almost motionless. This happens because Polaris is nearly perfectly aligned with our planet's axis of rotation. For observers in the northern hemisphere, it appears eternally fixed in its privileged position. This detail makes Polaris a cosmic beacon for navigators since ancient times. While all other stars spin in circles overhead, Polaris shines like a static point, always pointing north. This behavior isn't magic, but the result of its location in the sky, extremely close to the north celestial pole. That's what gives the star its unique reputation. But Polaris hasn't always occupied this central role. Earth's axis undergoes a slow wobble, called precession, which changes the star that marks the North Pole over thousands of years. Today, Polaris reigns supreme, but in the past, other stars played the same role. This means its importance is, in fact, temporary. Despite its privileged position, Polaris isn't perfectly aligned with the celestial pole. It sits just slightly off-center, tracing a tiny circle in the sky, almost invisible to the naked eye. Still, it's close enough that humanity has always treated it as the perfect guide. In the northern hemisphere, the farther north you are, the higher Polaris appears in the sky. At the geographic North Pole, it shines directly overhead, but in the southern hemisphere, the star disappears entirely, sinking below the horizon. That's why southern sailors and travelers had to rely on other constellations for guidance. This apparent stillness not only helped navigation, but also shaped culture. In many civilizations, Polaris was associated with constancy, stability, and even the sacred. Ancient peoples saw it as a fixed anchor in a sky of constant change. It was the cosmic nail holding the heavens steady. Modern astronomy confirms this privilege with precision. Using advanced instruments, astronomers can measure Polaris's tiny angular distance from the celestial pole. It's this remarkable closeness that makes it such a near-perfect reference point, a cosmic coincidence that profoundly marked human history. It's worth noting that Polaris isn't even close to being the brightest star in the sky. It doesn't rival Sirius, for instance. Its importance doesn't come from its light, but from its strategic position. And that position is what makes it the most special star of the Northern Hemisphere. Over the centuries, Polaris also became a literary and poetic symbol. Writers and explorers used it as a metaphor for constancy, fidelity, and guidance. Always there, steady, even when everything else changed. This symbolic image reinforced its role in the human imagination. Thus, Polaris isn't just a bright spot in the heavens. It represents the bridge between astronomy, navigation, and culture. A star that has guided and inspired simply by being in the right place at the right time, and that apparent fixed point is just the beginning of its deeper mysteries. The history of navigation. Long before satellites, modern compasses, and GPS, navigators relied on the stars to find their way. Among them, Polaris was the most reliable. Its constant position in the sky made it the perfect guide for anyone venturing across unknown seas. For ancient civilizations, it was literally the difference between being lost at sea and reaching the destination. The Phoenicians, masters of Mediterranean navigation, already used Polaris to guide their night journeys. They knew that by keeping the star in sight, they could safely adjust their routes. Later, the Vikings also relied on it during their daring voyages across the Atlantic. For these peoples, Polaris was a natural compass. But not only seafarers benefited from it. Nomadic desert tribes, such as the Bedouins, also used Polaris to navigate. In the midst of endless dunes and horizons with no landmarks, the star offered direction. A silent guide, always pointing north. regardless of the landscape. In ancient Egypt, priests also observed Polaris to align temples and pyramids. Its position in the sky helped them orient massive constructions with impressive precision. This shows that the star wasn't only useful for travel, but also for connecting human works to the cosmos. As centuries passed, Polaris kept its reputation. European explorers during the Age of Discovery also used it as a reference. It was a guarantee of stability amidst the unknown. Without it, many maps and routes might never have been successfully charted. Culturally, Polaris earned the status of a symbol of trust. Many peoples called it the guiding star, or the Star of the North. Its constancy became a metaphor for firmness and loyalty. In songs, poems, and legends, it appeared as a light that never failed, a true celestial lighthouse. With the invention of the magnetic compass, direct dependence on Polaris diminished, but never disappeared. Even today, in places where technology fails, sailors and scouts can rely on the star for orientation. It remains the simplest and most reliable reference in the heavens. Modern science confirms this practical use. The latitude of an observer in the northern hemisphere can be calculated by Polaris's height above the horizon. The farther north you go, the higher it appears in the sky, a direct relationship that makes Polaris a natural positioning tool. It's fascinating to realize how a single star helped shape trade routes, explorations, and even historical outcomes. Without its fixity, maritime expansion might have looked very different. Polaris in silence guided conquests and cultural encounters across millennia. Thus, the history of navigation is inseparable from the history of Polaris. It was compass, guide, and lighthouse, shaping human journeys since antiquity. And even in a world full of technology, it reminds us that the sky has always been our natural map, a hidden triple system. For a long time, Polaris was believed to be just a solitary star shining in the northern sky. But more detailed observations revealed an astonishing secret. It's actually part of a triple star system. This detail went unnoticed for centuries because its companions are much fainter and harder to detect. Only with modern telescopes and advanced techniques was the mystery finally uncovered. The first clue came in 1779, when astronomer William Herschel observed a nearby star and realized it wasn't alone. This star was later named Polaris B, a distant and faint companion, but gravitationally bound to the main star. Yet to the human eye, Polaris still looked like a single point of light, deceiving entire generations. Over a century later, in 1899, new evidence suggested that Polaris was hiding even more secrets. Astronomer William Wallace Campbell noticed variations in the star's radial velocity, hinting at the presence of another unseen body. It wasn't just coincidence. Polaris A seemed to have an even closer companion. In 1929, spectroscopic observations confirmed the suspicion. There was indeed a third star in the system, named Polaris AB. However, it remained unseen directly for almost 80 years until the Hubble Space Telescope finally captured images of it in 2006. This marked a milestone in modern astronomy. Today we know Polaris is a complex system. Polaris AA, the primary supergiant star, is accompanied by Polaris AB in a tight orbit. Together, they form a binary pair with a period of about 29.6 years. Further away, Polaris B orbits the inner duo very slowly, taking roughly 40,000 years to complete a single revolution. The distances involved in this cosmic dance are staggering. Polaris AB orbits just a few billion kilometers from the main star, while Polaris B lies about 386 billion kilometers away. For comparison, that's over 24 times farther than Voyager 1 has traveled from Earth in decades of spaceflight. Despite their differences in brightness, all these stars are bound together by gravity. Polaris B and AB are yellow-white dwarf stars, with masses similar to the Sun, but far less luminous. They orbit silently around the central giant, playing a crucial role in the system's balance. This triple system makes Polaris even more fascinating. Instead of being just a fixed guide in the sky, it hides a complexity invisible to the naked eye. The idea that the North Star is actually a trio of stars is a reminder that the universe is rarely as simple as it appears. The revelation also shows how astronomy advances with technology. Without instruments like Hubble, we might still think Polaris was solitary. The sky hides secrets that only patience and innovation can reveal. Polaris is a clear example that even familiar stars can surprise us. Thus, the title of the most confusing star in the sky becomes more justified. What seemed to be just a bright point is in reality a triple stellar system, complex, dynamic, and still puzzling scientists to this day. Polaris A, the main star. Among the three stars that make up the system, Polaris A is the true protagonist. It's the star we see with the naked eye, shining brightly in the night sky. Unlike its faint companions, Polaris A is a yellow supergiant, a rare type of star in an advanced stage of evolution. Its grandeur is what gives Polaris the distinctive glow we recognize. This supergiant has about 5.1 times the mass of the Sun and an impressive diameter, roughly 46 times larger. If placed at the center of our solar system, its size would reach more than halfway to Mercury. It's a colossal body, showcasing the sheer power of the later phases of stellar life. Polaris AA is classified as a Cepheid variable star. This means it doesn't shine steadily, but pulses in predictable cycles. Every 4 days or so, its brightness increases and decreases, as if the star were breathing. This peculiar behavior is fundamental to astronomy, since Cepheids are used as standard candles to measure cosmic distances. However, Polaris AA isn't a typical Cepheid. Its pulsations show irregularities that intrigue scientists. During the 20th century, the variation in its brightness dropped dramatically, something never observed in other similar stars. More recently, it began increasing again, defying all established models. In addition, its pulsation period has been lengthening at an unusually fast rate, about 4.5 seconds per year. For astronomy, that's an incredibly rapid change. Normally, such variations are only noticeable over millions of years, not within a few centuries of observation. Even more puzzling is that since 2010, this trend has reversed. Instead of lengthening, the pulsation period has been shortening each year. This sudden turnaround adds another layer of mystery, as no current model can fully explain it. Another intriguing detail is its mass. Some measurements suggest that Polaris AA appears less massive than expected for its evolutionary stage. This opens the possibility that it has lost material over time, perhaps through intense stellar winds or interactions with its companions. Recent studies also suggest that Polaris AA may host enormous star spots on its surface, similar to sunspots but on a colossal scale. These features may be linked to magnetic fields and could directly influence its irregular pulsations. Whether through its mass, brightness, or instability, Polaris AA is a puzzle for scientists. Each observation reveals a new, unsettling detail, and it's precisely this complexity that makes it such a valuable object of study. As the closest Cepheid to Earth, Polaris AA is essential for calibrating our cosmic measurements. But if we can't fully understand even this star, what does that say about our estimates for the rest of the universe? The mystery of Polaris AA may be pointing to deep flaws in our stellar models, the hidden companions. Although Polaris AA steals the spotlight with its intense brightness, its companions Polaris AB and Polaris B are crucial pieces in the puzzle of this stellar system. For a long time, their presence was only suspected until more sophisticated observations confirmed that the North Star was never truly alone. These hidden stars help explain part of the strange behavior of the giant primary. Polaris AB is the closest companion. It's a yellow-white dwarf with just over 1 solar mass. Its orbit around Polaris AA is tight, completing a revolution every 29.6 years. So close and faint, AB went unnoticed for centuries. Only in the 20th century, through spectroscopic techniques, did scientists begin to detect its existence. Polaris B, on the other hand, was discovered back in the 18th century. It orbits the entire system at a colossal distance, taking about 40,000 years to complete a single revolution. While easier to observe than AB, its luminosity is hundreds of times weaker than that of the primary star. For this reason, it has never been visible to the naked eye, remaining hidden from ordinary observers. These companions are fascinating not only because they exist, but also because of the impact they have on Polaris AIA. The gravitational interactions between them may be the key to understanding the irregular variations in the primary star's brightness. Many astronomers believe that orbital encounters between AIA and AB could influence its pulsations. Despite being faint, the companions also help test stellar evolution models. Since each has different masses and luminosities, comparing their estimated ages sparks heated debates. It's precisely this contrast that led to the famous age paradox, where Polaris AA appears far younger than Polaris B. From a historical perspective, the detection of these hidden stars also demonstrates how much our technology has advanced. The fact that we only managed to capture images of Polaris AB in 2006, thanks to the Hubble telescope, proves that even familiar stars can hide secrets for centuries. A reminder that the universe loves to surprise us. Another curiosity is that both Polaris B and AB are, in themselves, fairly ordinary stars, quite similar to the Sun in many ways. What makes them special is the context, being bound to a rare and unstable supergiant. Without them, Polaris would simply be another peculiar star. With them, it becomes a living laboratory of stellar dynamics. This trio also represents a risk of oversimplification. For a long time, astronomers treated Polaris only as an isolated Cepheid. But remembering that it is influenced by companions shows that part of its abnormal behavior may not be so inexplicable after all. The challenge is that we don't yet have models that fully account for all these variables. Culturally, the revelation that Polaris isn't solitary adds an almost poetic tone to its story. The star that guided humanity for millennia was never truly alone in its cosmic journey. Even if invisible, its companions were always by its side, silently orbiting. Thus, Polaris AB and B aren't mere side characters. They are essential to understanding why the main star behaves so strangely. And at the same time, they remind us that astronomy can never rely solely on what our eyes can see. The mysterious pulsations. One of the most intriguing features of Polaris is its condition as a Cepheid variable star. This means it pulsates in cycles, growing brighter and dimmer in a predictable rhythm. Normally, Cepheids follow a fairly stable pattern, but Polaris seems to enjoy breaking the rules. Its pulsations are among the strangest ever recorded in astronomy. Polaris's main cycle lasts about 4 days. During that period, its luminosity rises and falls smoothly, like a stellar heartbeat. This oscillation should remain steady, but over time, astronomers noticed something unusual: the amplitude of its brightness. The difference between its brightest and faintest points began to change. Between the 1960s and 1990s, this amplitude declined drastically, dropping from about 0.1 magnitude to less than 0.05. It was as if the star's pulsations were growing quieter, almost silencing a rhythm that should have remained constant. No theory of Cepheids predicted such behavior. But the surprises didn't end there. Starting around the year 2000, Polaris began to wake up again. Its amplitude increased once more, without any clear explanation. To this day, there's no consensus on why it behaves this way. Polaris acts as if it has a life of its own, defying every expectation. Another puzzling aspect is the change in its pulsation period. Instead of remaining steady, it had been increasing by about 4.5 seconds per year. For astronomers, this is an extremely rapid rate. Normally, such changes would only be noticeable on million-year timescales, not within just centuries of observation. Even stranger is that since 2010, the trend has reversed. Polaris's pulsation period has been shortening year by year, the exact opposite of what had been observed. This reversal left scientists even more baffled, since no current model explains such a sudden shift. Some suggest that gravitational interaction with Polaris AB might be disturbing the process. Whenever the two come closest in their orbit, the encounter could alter the supergiant's pulsations. But this hypothesis remains unconfirmed. Other studies point to factors such as mass loss or even strong magnetic fields. These changes make Polaris unique. No other known Cepheid has shown such erratic behavior over such a short timescale. This raises the question: is Polaris truly an exception, or are we witnessing a phenomenon that may be more common than we realize? From a practical standpoint, this is a major issue. Cepheids are critical tools for measuring distances in the universe. If Polaris, the closest Cepheid, doesn't follow the rules, how much can we trust the others? This dilemma makes the star a central piece in the debate over the reliability of the cosmic distance ladder. Thus, Polaris's mysterious pulsations aren't just an astronomical curiosity. They may affect how we calculate the age, size, and even the fate of the universe. A star that breathes in chaotic rhythms, reminding us that the cosmos still holds secrets far beyond our comprehension. Henrietta Leavitt and the Cepheids. In the early 20th century, a revolutionary discovery forever changed astronomy. Henrietta Swan Leavitt, an astronomer working at the Harvard Observatory, was studying variable stars in the small Magellanic Cloud. She noticed a striking pattern. The brighter a Cepheid was, the longer its pulsation period. This simple yet powerful relation opened the door to measuring cosmic distances in an entirely new way. Until then, humanity could only calculate nearby stellar distances using the parallax method, which is limited to a few hundred light years. With Leavitt's discovery, suddenly it became possible to measure millions of light years. Cepheids became true, standard candles, reliable tools for mapping the universe on a grand scale. Polaris, being the closest Cepheid to Earth, should have been the crown jewel in this process. Studying it ought to provide the most precise measurements for calibrating the period-luminosity relationship. However, the star refuses to cooperate. Its irregular pulsations and strange variations make it an atypical Cepheid, one that doesn't fit neatly into Leavitt's rule. Even so, Polaris remains essential. If we can understand its inconsistencies, we can refine our models further. After all, if the nearest Cepheid doesn't behave as expected, what about those much farther away? Solving the mystery of Polaris means gaining more confidence in the entire cosmic distance ladder. Henrietta Leavitt never lived to see the monumental impact of her discovery. Her work, initially overlooked, became one of the foundations for Edwin Hubble to confirm the expansion of the universe. Today, every observation of Polaris still carries the weight of her scientific legacy. Ironically, despite all our technological advances, the closest link in the cosmic ladder is also one of the most problematic. Polaris should be the star that helps us confirm measurements, but instead it behaves like an enigma. This paradox makes it a constant challenge. Scientists continue refining measurements of its brightness and period, trying to fit it into Leavitt's relation. But the irregularities persist, suggesting that additional factors may influence Cepheid pulsations, such as stellar rotation, magnetic fields, or mass loss. Still, Polaris retains its prominence. No other variable star has been studied as intensely. Its closeness makes it a living laboratory for testing theories. Even as the most confusing, it's also the one that can teach us the most. This story shows how a seemingly simple discovery can have enormous implications. Henrietta Leavitt not only opened the door to the cosmos, but also handed us a key we are still learning to use. And Polaris is the toughest lock for that key. In the end, the star that should have been the perfect example of Cepheids has instead become their greatest challenge. A paradox that honors Leavitt's genius and keeps alive the quest for answers at the heart of modern astronomy: the distance enigma. If there's one thing modern science should easily accomplish, it's measuring the distance to the star that has guided us in the sky for centuries. Yet with Polaris, nothing is simple. Determining exactly how far away it is has proven to be a true puzzle, full of contradictions. The most traditional method is stellar parallax, which measures the apparent shift of a star in the sky as Earth orbits the Sun. For nearby stars, it works quite well. But in the case of Polaris, hundreds of light years away, the shift is tiny, nearly impossible to measure with precision. In the 1990s, the Hipparcos mission tried to solve the issue. Its measurements placed Polaris about 434 light years from Earth. For a long time, that was the accepted value. But more recent observations from ESA's Gaia satellite suggested it might actually be 447 light-years away, slightly farther. The difference may sound small, but in astronomy, it's huge. Every extra kilometer alters fundamental calculations of luminosity, mass, and even the star's age. In other words, without a precise distance, all other estimates about Polaris are on shaky ground. To make matters worse, Polaris's brightness saturates detectors, making readings less reliable. Add to that its variable nature, plus the fact that it's in a triple system, and the measurements become even more complicated. It's like trying to hit a moving target that keeps changing shape. Independent studies have tried combining data from different methods, but the results still diverge. Some suggest Polaris may be closer than we think, while others argue it's farther away. There is still no universal agreement in the scientific community. This uncertainty has serious consequences. If we can't determine Polaris's distance with confidence, how much can we trust the larger scales that depend on it? The problem echoes through the very foundation of cosmology, affecting even calculations of the universe's expansion. Despite our technological progress, Polaris continues to outwit us. Even with state-of-the-art satellites, we can't seem to pin down something as basic as its true distance. It's ironic that the star most visible to the naked eye is one of the hardest to measure scientifically. Hope now rests on upcoming Gaia data releases expected in the next few years. With more refined measurements, we might finally untangle the knot. But until then, Polaris remains a reminder that the universe doesn't yield its secrets easily. This mystery reinforces its title as the most confusing star in the sky. There it is, shining steadily for all to see. But the moment we try to understand it deeply, everything becomes complicated. A cosmic riddle that challenges science while fueling our fascination with the stars. The contradictions of age one of Polaris's greatest enigmas lies in its age. When astronomers analyze Polaris A, the primary supergiant, everything suggests it's about 50 million years old. Yet its companion, Polaris B, appears far older, roughly 2 billion years. This discrepancy creates an uncomfortable paradox. How can two stars that seem gravitationally bound have such drastically different ages? Logic tells us that if they were born together from the same molecular cloud, they should have similar ages. But observations don't confirm this. Polaris AA looks far too young, while Polaris B has aged as expected. This stark contrast implies that something unusual happened in the system's past. One possibility is that Polaris B isn't actually a true companion, but rather a background star aligned along our line of sight, only appearing close by. However, calculations of its motion and gravity provide strong evidence that the two stars are indeed physically linked. Another explanation comes from the theory of blue stragglers. In this phenomenon, a star appears younger than it really is after undergoing a stellar merger. Two smaller stars may have collided and fused, creating a more massive star with renewed energy. This could explain Polaris A's apparent youth. If true, Polaris A didn't begin life as we see it today. Instead, it would have undergone a violent union, gaining extra mass and luminosity that make it look younger than its companion. Though plausible, this scenario remains speculative and difficult to confirm with certainty. The age discrepancy also raises doubts about our stellar models. Do we truly understand how stars like Polaris evolve? Or are factors such as stellar rotation, mass loss, and gravitational interactions distorting our analyses? These questions remain unanswered. Ongoing studies attempt to reconcile the data. Some astronomers suggest that measurement errors in distance or luminosity may be skewing conclusions. Others argue that Polaris AIA could be in a rare evolutionary stage that makes it appear younger than it really is. Regardless of the explanation, this paradox makes Polaris one of the most intriguing systems ever studied. The coexistence of a seemingly young star and an old one in the same system challenges our understanding of stellar lifetimes. It's as if the system were an anomaly in cosmic time. Culturally, this contradiction is just as captivating. The star that has guided humanity seems at once ancient and youthful, embodying a mysterious duality, a reminder that even our most precise science can be surprised by the cosmos. Thus, the age paradox of Polaris remains without a definitive solution. But perhaps it's this very contradiction that makes it so special. By defying our expectations, it forces us to look deeper and question even the things we thought we knew for sure. Unexpected changes in its period. Beyond the mystery of its age, Polaris also puzzles astronomers with its period changes. As a Cepheid star, it should pulsate predictably, with steady cycles of brightness. Yet over centuries of observation, Polaris has defied this rule in astonishing ways. For about 150 years, astronomers recorded that its pulsation period was lengthening by roughly 4.5 seconds per year. This was already unusual, suggesting that Polaris was evolving rapidly. Typically, such changes would only be noticeable on million-year timescales, not within a few human lifetimes. But in 2010, something even stranger occurred. The period began shrinking. Suddenly, Polaris reversed its trend, shortening its pulsation cycles. This unexpected change left astronomers baffled, since no current model can fully explain such a sharp turnaround. One hypothesis is that its close companion, Polaris AB, influences the giant's behavior. Each time the two stars reach their closest orbital point, gravitational interaction could disrupt the pulsations. Yet this theory remains unproven, and more data is needed to confirm it. Another possibility is that internal processes, such as mass loss or strong magnetic fields, are altering the star's dynamics. Recent studies even suggest that Polaris may host giant star spots on its surface, which could interfere with its cycles in unpredictable ways. These shifts make Polaris a unique case among Cepheids. No other star of its kind has displayed such erratic behavior in such a short timescale. This raises the question, is Polaris truly a rare exception, or could other Cepheids eventually reveal similar traits once studied long enough? The practical implications are significant. Cepheids are essential tools for measuring cosmic distances. If Polaris, the closest one, doesn't follow the rules, how reliable are the rest? This dilemma makes the star central to the debate about the accuracy of the cosmic distance ladder. Still, each anomaly presents an opportunity for discovery. Polaris reminds us that science advances through questions as much as through answers. Its unpredictability pushes astronomers to refine theories and look beyond established models. This strange behavior also underscores its title as the most confusing star in the sky. It not only guides sailors with constancy, but also guides scientists toward deeper questions. In the end, perhaps its true role is to challenge us to never stop searching. Thus, Polaris isn't merely an outlier, it may be the key to uncovering hidden complexities in stellar evolution. Its unexpected changes are not just puzzles, but potential pathways to new understanding of the universe. Possible stellar merger. Among the most intriguing theories to explain Polaris's anomalies is the idea that it's the product of a stellar merger. This phenomenon, known as the creation of a blue straggler, occurs when two stars fuse, forming a single one that appears much younger than it actually is. Polaris AA may very well be such a case. Blue stragglers were first identified in globular clusters. There, some stars stood out as hotter and brighter than they should have been, given the cluster's age. The most accepted explanation is that they were rejuvenated by the merger of binary stars, gaining new energy and a longer apparent life. Applied to Polaris, the idea fits. Its apparent youth may not be an error in measurement, but rather the result of a turbulent past, in which two stars fused into the supergiant we see today. This could solve the contradiction with its companion, Polaris B, which appears much older. A merger of this kind wouldn't only alter age, but also generate internal instabilities. This may help explain why Polaris displays such irregular pulsations. The fusion would leave scars inside the star, revealed as unpredictable variations in its brightness and period. The problem is that, so far, there's no direct evidence that Polaris went through such a merger. What we have are behaviors consistent with what we'd expect from a rejuvenated star. Confirming the hypothesis would require deeper observations of its internal structure. If proven true, Polaris would become a rare and valuable example of a post-merger star in an advanced stage. It would provide an unprecedented opportunity to better understand the evolution of binary systems and the consequences of stellar collisions, a field still full of mysteries. The merger hypothesis could also connect to its suspected mass loss. Rejuvenated stars often become unstable, shedding large amounts of material. This could explain why Polaris appears less massive than expected for its evolutionary stage. The idea also gives Polaris a poetic aura. The star that has guided humanity may, in fact, be the result of a violent union in the distant past, a cosmic collision that created the very beacon we follow in the sky. Even if speculative, this theory shows how far Polaris pushes science. It's not enough to call it strange. We must consider radical scenarios to make sense of it. Perhaps in the end, the merger is the missing key to its enigma. Thus, Polaris may not only be the most confusing star in the sky, but also a rare witness of how the universe reinvents itself. A reborn star, challenging the rules and reminding us that astronomy is, above all, the science of exceptions. Polaris and the expansion of the universe. If understanding Polaris is already important on its own, its relevance grows even more when we consider its role in cosmology. As a Cepheid star, Polaris should be one of the most reliable references for measuring distances in the universe. Yet its irregularities cast doubt on the very precision with which we measure cosmic expansion. The expansion of the universe is described by the so-called Hubble constant, which indicates the rate at which galaxies are moving away from each other. There are two main methods to calculate this value. One based on the cosmic microwave background, and another based on distance measurements using Cepheids and supernovae. The problem is that these two methods don't agree. The value derived from Cepheid-based methods hovers around 73 km/s per megaparsec, while the one from the cosmic background sits closer to 67 km/s per megaparsec. This discrepancy, known as the Hubble tension, is one of modern cosmology's greatest mysteries. And at the heart of this issue are Cepheids, including Polaris. If we can't fully understand the nearest Cepheid, how much trust can we place in measurements of those millions of light years away? Polaris should be the star that gives us confidence, but instead, its anomalies cast doubt on the foundation of our calculations. This doesn't mean the expansion of the universe is wrong, but it suggests our calibration methods may need refinement. Polaris's odd behavior could be the tip of the iceberg, hinting that there's still missing physics in our models of variable stars. Some researchers argue that solving the mysteries of Polaris could allow us to recalibrate the cosmic distance ladder with greater precision. That would directly affect the value of the Hubble constant, and by extension, our estimates of the universe's age and fate. Others, more cautious, suggest Polaris may be a rare outlier, not representative of Cepheids as a whole. Still, ignoring its warning signs would be risky. After all, science advances by confronting exceptions and trying to explain them. Either way, Polaris holds a strategic position in cosmology. It is both a problem and an opportunity. A confusing star that may be delaying resolution of the Hubble tension, but also a crucial clue to solving it. This situation is both frustrating and fascinating. The star that guided sailors across the seas may now be guiding scientists toward a revolution in understanding the cosmos. A reminder that even the brightest lights in the sky can hide profound secrets. Thus, Polaris is more than a symbol of constancy. It may also be the guardian of answers about the very rhythm of the universe. By deciphering its behavior, we may not only uncover the truth about a single star, but also about cosmic expansion itself. The future of Polaris. Although Polaris is today the North Star, its reign won't last forever. Like all stars, it is constantly evolving, moving toward increasingly unstable stages of its life. As a yellow supergiant, Polaris has already left the main sequence of hydrogen fusion and entered an advanced phase, which means its cosmic fate is sealed. With more than 5 times the mass of the Sun, Polaris will not end its life quietly. Unlike smaller stars that fade into white dwarfs, supergiants usually end in catastrophic events such as supernovae. We don't know exactly when this will happen, but Polaris's future will almost certainly be explosive. Such a dramatic end would have consequences not just for Polaris itself, but also for its companions, Polaris AB and Polaris B. A supernova shockwave could completely disrupt the system's dynamics, potentially flinging its neighboring stars into interstellar space. A violent ending for what now seems like a stable trio. Before that happens, however, Polaris will continue changing its pulsations and varying in brightness. Astronomers believe it may still go through phases of greater instability, possibly expanding even further before collapsing. This means the star will remain a fascinating subject of observation for centuries. Beyond its stellar evolution, there's also the matter of its position as the North Star. Earth's rotation undergoes a slow wobble, called precession, which gradually shifts the celestial pole. Because of this, Polaris won't always occupy the role of the North Star. Roughly every 26,000 years, the celestial pole completes a circle, pointing to different stars over time. This means that in a few thousand years, Polaris will no longer be the guiding point in the sky. Other stars, such as Vega, will take its place in the future. This cosmic cycle shows that even the firmest references are temporary. To our ancestors, Polaris seemed eternal, but modern astronomy reveals that its importance is fleeting. On a cosmic scale, it's only a brief chapter in Earth's celestial dance. Even so, Polaris will remain special for our era. It will continue shining as the guiding star for centuries to come until Earth's axis drifts enough to hand over the role to another star. A long reign, but not an everlasting one. The future of Polaris is therefore doubly intriguing. On one hand, its stellar evolution points toward a violent and luminous finale. On the other, its place in the sky shows that its role as a guide is also temporary, a reminder that nothing in the universe lasts forever. Thus, Polaris is not only the most confusing star of today, but also a symbol of an uncertain tomorrow. Its destiny combines cosmic drama with inevitable change, cementing its place as one of the most fascinating stars in astronomy. The dance of the celestial poles. The reason Polaris is the North Star is not just coincidence, but the result of a phenomenon called precession. As Earth spins like a top, its axis does not stay perfectly fixed. Instead, it wobbles slowly in a circular motion over thousands of years, shifting the position of the celestial pole. This cosmic dance ensures that Polaris won't always be the North Star. About 14,000 years ago, for example, the star Vega in the constellation Lyra occupied the position of the North Star. For the people of that time, it was Vega that remained fixed in the sky. In the future, Earth will repeat this cycle, and Vega will once again take the role in roughly 12,000 years. This motion is caused by gravitational forces from the Moon and the Sun acting on Earth. Just like a spinning top that wobbles as it turns, our planet also oscillates, gradually altering the orientation of its axis. The full cycle of precession takes about 26,000 years. This means Polaris is the North Star for only a small fraction of cosmic history. On human timescales, it seems eternal, but in astronomical terms, it's only a moment. For our distant descendants, the guiding star in the night sky will be completely different. Despite this transience, the current alignment is remarkable. Polaris sits almost perfectly above the celestial pole, a rare coincidence. This made it an ideal reference for navigation, especially during the era when humans relied heavily on the stars to find their way. The cycle also carries cultural significance. Different civilizations in different eras have had different guiding stars. What is Polaris to us today was Vega to ancient peoples, and one day another star will play that role. Each epoch has its own North Star. Scientifically, precession also helps explain changes in ancient records. Astronomical alignments of temples and pyramids, for instance, may seem off today but were precise at the time they were built. The dance of the celestial poles shifts the entire sky over millennia. This oscillation even affects our astronomical calendar. The positions of zodiac constellations slowly drift because of precession. Over thousands of years, the night sky transforms dramatically. Polaris is just one actor in this vast mechanism. Interestingly, in a few thousand years, no star will sit as close to the celestial pole as Polaris does now. This means future navigators won't have such a precise reference. We are living in a privileged era with a nearly perfect guiding star. Thus, the dance of the celestial poles reminds us that even the night sky, which seems so unchanging, is constantly shifting. Polaris is only the star of the moment, a temporary marker in an eternal spectacle of movement and change. The impact on astronomy. Polaris is not just a bright point in the sky, nor only the guiding star that helped navigators and civilizations for millennia. It is, above all, a living laboratory for modern astronomy. Every enigma it presents, whether its contradictory age, its unpredictable pulsations, or its uncertain distance, directly challenges our stellar and cosmological models. Cepheids, the class of stars to which Polaris belongs, are fundamental for measuring the universe. They serve as standard candles, calibrating cosmic distances and supporting the calculation of expansion rates. But if the closest Cepheid behaves irregularly, it casts doubt on the reliability of the entire method. It's as if the very base of our cosmic ruler were unstable. This instability could mean two things. Either Polaris is a rare exception, a case to be treated as unique, or our theories remain incomplete, needing to account for factors like mergers, magnetic fields, and mass loss. In both scenarios, studying Polaris is essential for refining science. The impact is cultural as well. The fact that such a visible and important star remains an enigma shows that the sky hasn't lost its ability to surprise us. Polaris continues to spark the same curiosity that fascinated ancient peoples, though now with even more complex questions. Future generations of telescopes and satellites promise to reveal crucial new insights. The upcoming data releases from the Gaia mission, for example, may bring more precise distance measurements. This could untangle one of Polaris's greatest mysteries, and perhaps open the door to new ones. Another impact lies in the way Polaris forces us to confront uncertainty. Instead of easy answers, it shows us that science is a continuous process, full of revisions and unexpected discoveries. A lesson in cosmic humility. Even a familiar star can hide immense complexities. Practically speaking, every study of Polaris reverberates into other fields. Models of stellar evolution, supernova predictions, estimates of the universe's age, all depend, directly or indirectly, on the accuracy we seek in this star. Polaris is a central knot in a much larger web of knowledge. Its symbolic position in the sky also adds weight. Even though it won't always be the North Star, Polaris represents the balance between stability and change. A reminder that in the cosmos, nothing is truly fixed, but everything can serve as a guide if we know how to interpret it. Thus, Polaris's impact on astronomy is both profound and multifaceted. It is at once a problem and an opportunity, a star that confuses and inspires. By forcing us to rethink what we know, Polaris guides us not just across the seas, but through the mysteries of the universe itself. In the end, perhaps that is the greatest legacy of the most confusing star in the sky, showing us that mystery is the engine of science, and that the more enigmatic a star appears, the closer we may be to discovering something fundamental about the cosmos. And ourselves, Polaris may look like just a bright point in the sky, but it hides mysteries that challenge what we know about stars, and even the universe itself. It has guided navigators, inspired cultures, and today it leads scientists in the search for deeper answers. Its contradictions show that the cosmos still holds secrets beyond our understanding. And perhaps that is what makes it so fascinating. A star that never stops surprising us. Tell me, of these 10 facts about Polaris, which one intrigued you the most?